Hi there, Andrew Dunkley again with another episode of Space Nuts, and it's good to have your company. This is a Q&A edition. This is where we answer your questions if we can. If we can't, we just pretend to. We've got questions about light and redshift today. We're also going to talk gas giants, expansion of the galaxy versus, or expansion of the universe versus galaxy collisions, and the future of navigation reference points. How are we going to do that when we start going further and further out? Those questions will be answered or they'll be faked. We're not sure yet. Deep Fake Radio coming up soon on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9, ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And he's here again like a fly on a piece of meat. Hello, Fred.
Thanks, Andrew. Thanks.
Professor Fred Watson, astronomer at large. Nice to see you.
Yeah, that's right. It's nice to see you too, I think.
Look, I have enough digs at Hugh. I thought maybe I should just...
That's fine. Yeah,
land a left hook for a change. It always comes back and hits me though eventually. So yeah, I can take it. I'm tough. Let's go straight to our questions. Our first question today, Fred, comes from Mario in Melbourne. He likes to go go-karting. Hi, Fred and Andrew. Hoping you can help explain why, if light itself doesn't experience time, how can it redshift? Doesn't redshifting imply it changes somehow, which implies it must have been subject to time? Or is this some sort of relativity witchcraft where we as observers experience time and the redshift, but the photon itself somehow in all states, it can be simultaneously or something like that, simultaneously or something like that. Appreciate you unscrambling my brain on this one. Still listening from the far start. Keep up the great show, Mario from Melbourne. I think we've kind of had variations of this question come up in the past. People sort of have trouble differentiating between light and time and what's going on out there. Can you shed some light on this one, Fred?
I'm sorry, I'm completely in the dark about this one.
Oh, bull.
It's a good point though, and so it's made me, got the old cogs working to try and work out what's happening, because that's right. Because light travels at the speed of light, which is the fastest speed anything could travel through the universe. It does not experience time. A photon of light does not experience time. And yet they change. And you're right. Mario is correct that we do see photons changing, because the photons that we are now receiving from distant galaxies, for example, are highly redshifted. They've become redder photons. Now, what that corresponds to is a loss of energy which results from the expansion of the universe. And so I think I'm right in saying that the photon doesn't notice that. It doesn't know that it's lost energy because it doesn't experience time. So I think, in a sense, the loss of energy, which, by the way, just filters out into the universe, apparently. Normally, that's where it goes. It's, I think that is a property of the observer, the fact that we're observing this thing. The photon, to the best of my understanding, doesn't care. It arrives at the same time as it left, because it doesn't experience time. But it might be surprised that the place where it arrived at is very different from the place where it left at in terms of the energy balance and what's happening there. I'm not sure whether I'm making much sense here, Mario, but that's my understanding of the situation.
Okay. It is a bit complicated. It'd be nice to be a photon if you're doing a long-haul flight, because if you didn't experience time, you wouldn't have to worry about a 20-hour flight to Turkey, for example.
No, you wouldn't. That's nothing.
Or anything like that.
Some of the places we go.
Yeah, all over the place. Yeah. We hope we unscrambled your brain, Mario, because it is a bit of a scrambly issue. But photons don't experience time, and they don't know that they're losing energy. It's sort of like old people.
Yep.
Oh boy. Go to hell
It's
for that
funny
one.
you should say that. No, look, I can vouch for that.
I'm starting to experience that myself. Yes. Thanks, Mario. Let's move on to our next one. This comes from Nigel.
Hi, Fred and Andrew. This is Nigel from Brisbane, Australia. I have 2 questions about our gas giants, Jupiter and Saturn. I want to know, beneath all that gas, is there a rocky planet? And if so, how big are they in relation to the Earth? Okay, thank you. Love the show. Keep up the good work.
Thanks, Nigel. Look, it's theory, isn't it, Fred? We don't know for sure what's down deep in those gas giants, but there might be something.
Well, you've absolutely answered the question, Andrew.
Okay, we'll move on to the next one from Raul.
Nigel's question is, it's one that many astronomers and planetary scientists ask because we don't know. We don't know the answer. The modelling suggests that because of the way we believe planets are formed, that there should be a rocky core underneath all that gas, that it should be quite massive, maybe with a fair degree of water ice involved with it as well. Although some of the papers that I've read suggest that there might be something called metallic hydrogen at the centre of these gas giants. I'm not sure what that means. Probably means hydrogen in a state where it can conduct electricity. So that's it's a question that's really at the forefront of knowledge. So you and me both, Nigel, I wonder what's at the centre of these gas giants and how big the central core might be, if there is one, which we assume there is.
Yeah. I mean, gas giants, to a certain degree, what could have been stars had their formation happened in a bigger, better way. At what point do they reach in size or structure where they wouldn't have a solid core? Like, would a brown dwarf have a solid core, perhaps?
Certainly a brown dwarf would have a core, and it probably wouldn't be solid either. More similar to what the sun's core we think is like, compared with what a planet's core is like. So brown dwarf has nuclear reactions taking place, but they're low-level ones. They're something called deuterium burning, and that doesn't generate anything like the same amount of heat as the hydrogen process that's going on at the centre of our sun. So at the centre of the sun, you've got this ball of energy, very, very hot, radiating gamma ray photons out, which eventually find their way as visible light out to the surface. The brown dwarf, you've got low-level radiation, which finds its way to the surface. With a gas giant, though, we don't know. That's the thing. We really don't know what the core would be like. The thinking is that they are cold enough to have a solid core, that you're not talking about a ball of energy. But we do know, again, that there are nuclear actions taking place for example, in the core of Jupiter. Jupiter radiates 1.8 times more heat than it receives from the sun. And that's coming from maybe uranium fission or something like that happening down there in its interior.
Yeah. Wow. Do they have a theory, yes. If Jupiter has a core, do they have a theory on how big it is compared to Earth?
Probably. But look, I'm going to take a punt and say, yes, people probably do think it is about the size of Earth. I'm sure I've heard that kind of suggestion before. Because remember, Jupiter's about 11 times the diameter of Earth. So.
Yeah. Wow. All right. Jury's still out, Nigel, but
Yep,
it's a maybe, could be, dunno type of scenario. But thanks for the question. Sorry?
Yeah. Nothing to do with us.
Nothing to see here. This is Space Nuts, Andrew Dunkley with Fred Watson, Professor, Astronomer at Large, great guy. Now let's take a little break from the show to tell you about our sponsor, NordVPN. Now, not so long ago, I did a bit of a speed test, just ad hoc speed test. Didn't plan it, just went ahead and did it on the spot to prove that you do not lose very much speed using NordVPN on your desktop computer or your laptop for that matter. I thought I'd test it on my mobile device, which I haven't done in recent times. So I've got my phone here. I've got the speed test icon going, so I'll do a speed test without using NordVPN. So here we go. And it is connecting and doing what it does. Boom. Okay, there's it peaked at 135, but it's hanging around the 115, 116 mark. So I'm going to close that. Then I'm going to connect NordVPN to my phone. And we are ready to go via NordVPN this time. And I'll hit go and we'll see what happens. So this is going via Central Australia. And I'm still achieving speeds of about 70 to 80 megabits per second. I am losing a bit, but it's not a lot. That's still really good speeds on a mobile network. The upload speed is actually faster. My upload speed is pushing up towards 10 megabits per second. Now it's just hitting 11. So with NordVPN, I lose a bit on the download, but I gain almost double on the upload, which is extraordinary. Now, they've been our sponsor for quite some time. I use all their products. I've signed up. There's a special URL if you're interested in looking at NordVPN as a Space Nuts listener. To get the best discount off your NordVPN plan, go to nordvpn.com/spacenuts. Our link will also give you 4 extra months on the 2-year plan. There's no risk with Nord's 30-day money-back guarantee. And I'll add the link to the show notes. And they back their products, not just the high-speed VPN, but the malware protection, the tracker, ad blocker, cross-platform password manager. That's my favourite thing in the world. The data breach scanner and a terabyte of cloud storage. Depending on which plan you get, you can combine all those things. So nordvpn.com/spacenuts is where you go, and check out the deal today. You won't regret signing up with NordVPN. Now, back to the show.
3, 2, 1.
Space Nuts.
Okay, our next question, Fred, comes from Raul.
Hi, guys. Raul from California here, and a big Chelsea fan. I know you were talking about American football, but I do like European football. Had a question for you. If the universe is ever expanding from the Big Bang, then all the galaxies would be moving apart from each other. But I recall seeing on a show that galaxies could one day collide. Does that mean that the universe is stopping its expansion or slowing its expansion, allowing the gravity of galaxies to then collide? And if that is the case, will the universe one day stop expanding and start to contract upon whatever the hugest big black hole in the middle of the universe really is? Thanks a lot. You guys do great. Love listening to it. Newbie to the show, but love what you do. Bye.
Thank you, David. Chelsea. I'm a Liverpool.
It was Raul.
Oh, sorry. Yeah, David's next. Raul, thanks for that. Yes, Chelsea fan, but yeah, we'll forgive you for that. I'm a Liverpool fan myself. Do you follow English Premier League or Scottish League?
Slightly, yeah. Only, some of the bigger teams. I'm always interested in what they're doing. I've got a son-in-law and a couple of grandsons who are absolutely mad Manchester United freaks, and various other football teams. I never really got heavily into football. I could never remember which way I was supposed to be kicking the ball, so it wasn't my scene really. It takes an interest.
Yeah, I played soccer for 10 years, never won a thing. Didn't even win the raffle. Anyway, Raul's asking about the universe and its expansion versus galaxy collisions, basically. And, is the expansion slowing or stopping? And is that why galaxies are going to crash into each other? Is it all going to sort of fall back into a giant black hole in the middle? We've had variations of questions like this over the years. It's one that always spawns a lot of interest.
It does, doesn't it? And there are actually two things going on here, I think, in Raul's question, because he's quite right that some galaxies do collide with each other. And in fact, we are in pole position for a collision with Andromeda that might already be happening.
In fact, we talked about it the other day. They're actually sort of, tickling their fingertips at the moment because of that giant gas balls that's been revealed.
Indeed. So, and so why are they colliding if the universe is expanding? Because both those statements are true. The universe is expanding and the two galaxies are colliding. And that's because on the scale of the distance between us and Andromeda, which is 2.5 million light years, the expansion of the universe is negligible, more or less. The universe is expanding, but over a small distance like that, what becomes the dominant force is gravity, and the gravitational pull between the Milky Way and Andromeda are easily enough to overcome the fact that they're being pulled apart much more gently by the expansion of the universe. So, and that's we give it a term. We got a name for the individual motions of galaxies, kind of superimposed on the expansion of the universe. We call it their peculiar motions, and it's so the peculiar motion of Milky Way relative to Andromeda is they're colliding together, and they will collide. Whereas the expansion of the universe is trying to pull them apart, but at a much, much slower rate, if I can put it that way. It's only when you look on the big scales that you see the real effects of the expansion of the universe, things that are billions of light years away from us rather than just a couple of million. Basically, Raul's right. Until 1998, we used to think that eventually the gravitational pull of everything in the universe would slow down the expansion, and the universe would indeed collapse on itself in what we always call, Andrew, the
Gnab-Gib.
The Gnab-Gib, exactly.
Big Bang backwards.
Big Bang, that's right. Brian Schmidt's praise, the Gnab-Gib. We used to think, you often called the Big Crunch as well. That was the thinking, and it was when Brian Schmidt and his colleagues and other colleagues in the United States, when they discovered the accelerated expansion of the universe, that the possibility of the Gnab-Gib was thrown out the window, because the universe is, as far as we know, going to expand forever, and there isn't enough stuff in it for its gravitational pull to halt the expansion. And part of that is because we think that space itself has an energy. We call it dark energy, and the more space you have, the more energy you've got, and that energy is trying to push things apart, to push the universe into ever faster expansion. So, yes, it looks as though that Big Crunch scenario has gone out the window, but it was very popular in the 1970s and 80s.
So what's the opposite to a Big Crunch? It's a Gnab-Gib. Gnab-Gib.
Yes, that sounds right, yeah.
Yeah. Someone's going to ask again, because we've had the question before, but if the universe keeps expanding and it's filling with dark energy, where's the energy coming from? How's that fueling itself? We don't know.
We don't. It comes out of space.
Yeah, it comes from somewhere. Yeah. People say it's coming from dark matter, but they're not related. They're just badly named.
Yes, they are. That's correct. I mean, maybe it's coming from outside, if there's multiverses.
Oh, that would be something, wouldn't it? We should just go and have a look. Simple.
That's a good idea.
Yeah.
Send Voyager.
It's on its way. We just have to sit here and twiddle our thumbs and just wait a little while. And then we'll know if the batteries don't run out. Did we finish with Raul? I think so, yeah.
We did, yes.
All the best, Raul, and I hope Chelsea doesn't win as much as Liverpool. Let's go to our final question. And this one comes from, this is David. Wow, what a coincidence. Hi, love your podcast. I live in the lovely dark city of Tucson. That'd be the Arizona variety, I imagine. My question, I assume astronomers use the sun as a center of reference, but what about the future when we want to travel somewhere else? Everything is moving and it's a no-body system. It's hard to know exactly where anything is going to be if you wait long enough. How will you tell our colony on Proxima Centauri where to go or where to look when it takes 4.2 years for them to get the message? That's from David. I like this question. It's a long-term future problem when we're living in other parts of the galaxy outside our own solar system. We've made the giant leap and ended up on one of those perfectly normal planets around the Alpha Centauri system, and we want to come back. How do we find our way back? I mean, we can find our way there, so I assume we can find our way back. Mathematics would be my answer to this one.
Well, it is. It's a good question, actually, and it has a real significance to it because we already need reference points like that for things like GPS. Satellite navigation systems, space navigation, even in the small distances within our solar system, you need fixed reference points. And what we use are the things on the sky that move least and are bright, and they are quasars. So quasars are very bright sources, but they're at very great distances, so distant that nothing we could ever do in terms of our movement would change their positions on the sky. And so quasars have formed the fundamental reference system that's used in astronomy, actually, as well as for navigation. We use them to set up basically reference systems for measuring galaxy positions, star positions, things of that sort. You use something that's not going to move, and the quasars don't move because they're so far away. So It's already there, David, and hopefully when you leave Tucson and head out towards Alpha Centauri, you won't need to have any worries that you'll lose your way home. You'll find your way back.
Yes, and don't ignore the sign that says next fuel stop, 2 billion kilometres. You really don't want to skip that one because it's a long way to the toilet, let's face it. Yeah. Yeah, all right. I didn't realise it'd be that easy, Fred. It's good to know.
Yep.
We just got to perfect the engines that enable us to travel far distances in a bit of a hurry. That's probably the bigger challenge than the navigation. Thanks, David. Great question. And if you have a question, please send it in to us via our website, spacenuts.io. You thought I was going to say spacenutspodcast.com, didn't you? Yes, well, that counts too. You can use both. They all end up in the same place. And you can send us a text or audio question just by clicking on the AMA tab. And if you've got a device with a microphone, you're all set. Don't forget to tell us who you are and where you're from. And don't forget to leave your reviews on whatever platform you use to listen to us. And social media, follow us, like us, subscribe wherever you are. We'd love you to make our little family a little bit bigger. And don't forget about the Space Nuts podcast group on Facebook. It's always growing. It's growing like a blob of gas in a nebula or whatever it is. It's where you can sort of chat with like-minded people who follow Space Nuts. Talk to each other, ask each other questions, share your astronomical photographs and stories. It's growing at a rate of knots, it is, Fred. And thank you for your company today, Fred, and thanks for tolerating my stupidity and answering all those questions.
That's all right. I can live with that, Andrew. No doubt we'll continue to do so. Keep up the good work. It's always great to talk. Thanks a lot.
We'll see you soon. Professor Fred Watson, astronomer at large, and the not Professor Hugh. Thank you to him for helping out Not Today. And we'll see you very soon. Andrew Dunkley signing off. We'll catch you on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.